Good morning. So, in the last class we started our discussion on the problem involved with dimensionality of the feature vectors, and we have said that when the feature vector dimension is quite large, then the computational complexity becomes very high, because computation of the discriminant function for different classes for each of the classes is proportional to d square, where d is the dimension of the feature vector. And when we have c number of such classes, then obviously the amount of time that has to be spent to decide the class, we have to compute the discriminant function for each and every class. So, the total computation time becomes of the order of c into d square, and you can easily understand that in most of the real life situations, the dimension of the feature vectors becomes of the order of 100 or 200 or so. And in that case, what will be the amount of computation involved to classify an unknown feature vector, because for every unknown feature vector we have to compute the discriminant function corresponding to each and every class, and then we have to decide to which class that unknown feature vector has to be classified based on which particular discriminant function gives the maximum value. So, in the last class we have discussed about this dimensionality reduction problem, and we have said that PCA or principal component analysis is one of the techniques by which the dimension of the feature vectors can be reduced, because the principal component basically gives you those principal components which are most useful to describe the feature vectors. Okay. So, though the principal component analysis that gives you the features, that reduces the dimensionality of the features by taking projection on lower dimensional space, either in single dimension or in multiple dimension, and we have seen that those directions are nothing but directions of the eigen values of the scatter matrix or covariance matrix of the data set, and we take those eigen vectors corresponding to the maximum eigen values, so that the error while doing the projection is minimized. Now, while doing so, these feature vectors in lower dimension that we get, they are the best representations of the original feature vector in terms of the squared error sense. Okay. We ensure that the sum of squared error when we project that higher dimensional feature vectors onto the lower dimension following principal component analysis, the sum of squared error will be minimum. However, it does not necessarily mean that those projections will be the best projections for separating different classes, because when we go for classification, we have to ensure that the feature vectors belonging to the different classes, they are well separated. Okay. So, while the principal component analysis tries to find out the projection directions which will give you best representation of the data set in minimum squared error sense, but MDA or multiple discriminant analysis tries to find out the projection directions. So, that if I take projections in those directions, I try to ensure that the data belonging to different classes or the sample vectors belonging to different classes, they are well separated in that projected space. Okay. So, today what we are going to discuss is this multiple discriminant analysis or MDA. Okay. So, this is also a projection technique, but when we try to find out the projection directions, we try to ensure that the data in the projected space, they are well separated. Now, why the principal component analysis does not guarantee you that sort of separation? Let us just take a sample situation, say something like this. Suppose I have two dimensional feature vector, one is feature component x 1, the other feature component is say x 2. Okay. And the data distribution, let us assume, is something like this. So, this is the data belonging to this space, the training samples that you get, that belongs to one class let us say this is class omega 1, okay, and the other set of training samples which are given, they may be something like this. Suppose this set of samples belong to class omega 2. Okay. Now, when you do principal component analysis, the principal component analysis takes the projections of data onto a direction which are aligned with the eigenvectors. Okay. So, in this case, the direction of the eigenvector having corresponding to the maximum eigenvalue will be something like this, because this is the direction in which the spread is maximum. Okay. So, on this, if I take the projection, let me draw the diagram somewhere over here. So, if I take the projection, you find that this set of data will be projected into this space, okay, whereas the data classified as labeled as belonging to omega 2 will be projected into this space. Okay. So, as a result, you find that I have a region where the data both from class omega 1 and class omega 2 they are intermingled. Okay. That means, taking this example, we can say that when I take the projections along the directions of along the directions of eigenvectors, it does not necessarily mean that the data will be well separated in the projected space. Whereas, if I take the projection direction like this, suppose I take this as the projection direction. We have discussed earlier that for best representation the projection should be orthogonal projection. Okay. So, if I take this projection direction, in that case you find that this set of data will be projected into this space, whereas this set of data will be projected into this space. And now, these two sets of projected data, they are well separated in the projected space. Okay. So, while principal component analysis tries to find out this direction, this projection direction, the multiple discriminant analysis tries to find out this projection direction. Okay. So, what does it practically mean? Let us assume that we have got two printed characters. One is say printed character O, other one is printed character Q. Okay. So, when I take the principal component analysis, the principal components actually tries to capture the gross features of the patterns, and while doing so, it may ignore the feature, this subtle feature corresponding to this tail, whereas this tail is most important to discriminate between O and Q, whereas principal component may ignore the feature corresponding to this tail part, and unless I have that information, I cannot discriminate between O and Q. Okay. So, that is the drawback of principal component analysis, though it gives you the best representation of data onto the projected space in minimum square sense, but it may not be the best projection so far as separability of the classes are concerned. Okay. So, that is the aim of the multiple discriminant analysis. And when we discuss today, I will take a specific case of multiple discriminant analysis that I will consider, that suppose I have got only two classes. Okay. And the approach taken for this multiple discriminant analysis to separate between two classes or to design a classifier which can classify between two classes after taking the projections onto lower dimensional space, that is what is called Fisher discriminator. So, let us see what is this. Yeah, they will pass through the mean of the samples, but what I have shown is just the projection direction. Actually, the line will pass through the mean of the samples. I have just shown the projection direction, not its exact position, and then tried to see that, because even if I pass this line to the mean of the samples, even then the same problem will occur. Either the projection will be downwards or the projection will be upwards, but the same problem will exist. Okay. I just have done it for the clarity of the figure, that is all. Okay. So, let us assume that we have n number of d dimensional feature vectors. Which are say x 1, x 2 up to x n. Okay. And these feature vectors are partitioned into two different sets. One is set D 1 consisting of n 1 number of feature vectors which are labeled as class omega 1, because we are going for supervised learning though. So, I have out of this n number of feature vectors, n 1 number of feature vectors, where obviously n 1 is less than n 1 number of feature vectors. I say that these feature vectors are in the set D 1 and these feature vectors are labeled to belong to class omega 1. Okay. Similarly, I have another set D 2 consisting of n 2 number of feature vectors, and these feature vectors are labeled as class omega 2. So, obviously, n 1 plus n 2 in our case will be equal to n. Okay. N is the total number of feature vectors partitioned into two subsets, one consisting of n 1 number of feature vectors coming from class omega 1. I am calling that set of feature vectors as D 1, and the other one is n 2 number of feature vectors coming from class omega 2, and I say that this set is set D 2. Okay. And suppose I take a projection direction W, okay, direction of projection, where I assume that modulus of W is equal to 1. That means, this is an unit vector in the direction of projection line. Okay. So, given this, a feature vector x I, when I take its orthogonal projection, because as we said that the orthogonal projections are the best projections. So, whenever we talk about projection, we will talk about orthogonal projection. So, when I take orthogonal projection of the feature vectors onto this line, suppose I take a feature vector x I, take the orthogonal projection onto this projection line, I get projected vector y I. Okay. So, here this y I will be nothing but W transpose x I, because W is the unit vector in the direction of line of projection, okay, and x I is the feature vector in my original space. When I take the projection of this in the direction of W, I get W transpose x I, and the projected vector is y I. Okay. So, when I have this n number of samples x 1 to x n, the projections of this onto this projecting line will be y 1, y 2 up to y n. So, each of these I can compute following this formula. So, here just y varies from I varies from 1 to n. Okay. So, these are the projected vectors that I can have after taking projection in the direction of W. Now, coming to the sets D 1 and D 2, okay, I can find out the mean M 1, which is nothing but mean of the samples in class D 1, and obviously, this M 1 is equal to 1 upon N 1 because n 1 is the number of samples in class D 1, then summation of A x for all A x belonging to set D 1. Okay. I take all the samples from set D 1 and average of that gives me the mean M 1. Similarly, M 2 is nothing but 1 upon N 2 summation of x for all x in set D 2. Is that okay? Now, when I compute the projections of these mean vectors, suppose the projected mean vector M 1 I write as M 1 hat. Okay. This M 1 hat is nothing but 1 upon N 1 into summation of y for all y belonging to say set R 1. Now, what is this R 1? When I have all these projected samples, projected vectors y 1 to y n, now the projected vectors which are projections of these n 1 number of samples, I call that set as set R 1. Okay. So, this set is the projected vectors of these n 1 number of samples. Okay. Similarly, I say set R 2, which is the set of projected vectors, set of these n 2 number of projected vectors. Okay. I call this set R 2, right. So, here this M 1 tilde, which is the projected mean, is nothing but 1 upon N 1 sum of y for all y belonging to class R 1, and this y is nothing but 1 upon N 1 summation of W transpose x, okay, for all x belonging to set D 1. Okay. I can take this W transpose out of this summation, because it does not depend upon the samples. Okay. So, I simply get 1 upon or W transpose, let me put 1 upon N 1 W transpose summation of x for all x belonging to set D 1, which is nothing but W transpose M 1. Okay. So, that is quite obvious. So, projection of mean of the vectors in set D 1 is nothing but W transpose M 1. Okay. In the same manner, I can compute the projection of mean of samples in set D 2, which is nothing but M 2 tilde. If I follow the same procedure, it will simply be W transpose M 2. Okay. So, M 1 tilde, that is the projection of M 1 onto the direction of W, is nothing but W transpose M 1. Projection of M 2 onto the direction of W is W M 2 tilde, which is nothing but W transpose M 2. Okay. Now, what is the distance between these two projected means? That is nothing but, so the distance between projected means is nothing but mod of M 1 tilde minus M 2 tilde. Okay. This is the distance between these two projected means, or difference between the two projected means, which will be simply mod of W transpose M 1 minus M 2. Okay. So, this is quite simple. Now, find that I can increase the distance between m 1 tilde and m 2 tilde by simply scaling up w. Okay. Here I have assumed that modulus of w is equal to 1. If modulus of w is more than 1, then the distance between m 1 tilde and m 2 tilde will go on increasing. As I increase the scale factor of w, the distance between m 1 tilde and m 2 tilde will increase, and that ensures that I can increase the separability between the two classes. Okay. But the question is, how much should I increase the separation between the two classes? Should I go on increasing indefinitely? Obviously, that is not justified or not very logical, because how much difference between m 1 tilde and m 2 tilde that I need for good classification depends upon what is the variance of the samples within set D 1 and what is the variance of samples within set D 2. Okay. This variance will indicate that what should be the difference between m 1 tilde and m 2 tilde. The reason is very simple. If I take that distribution, suppose I have two distributions like this. This is m 1, this is m 2. Okay. This is my x and this is say p x given omega. Okay. We said the error of classification is nothing but the area bounded between these two density curves, probability density curves, which is this shaded portion. Okay. Now, if the variance of the probability of the data distribution is quite large, okay, that means I have variance something like this. Okay. The other one is like this. So, this is my x, this is p x given omega, okay. This is m 1 and this is m 2. Okay. Here the variance or the standard deviation of the data within the two different classes are quite large. So, the curve has become very flat and the error is this. Okay. So, when I have this sort of distribution, you find that I should have the difference between m 1 and m 2 to be quite large, so that the error of classification is reduced. That means, these two curves should be wide apart, right. Whereas, if I have distribution of this form where the variance is very small, m 1 is somewhere over here, m 2 is somewhere over here. Okay. So, in this situation, I do not need that much separation which I need in the first case. Here the separation between m 1 and m 2 can be much less than this, but even then my error, the total error will be under control. Okay. So, how much should be the difference between two projected means in the reduced space? That should be relative to the variance or standard deviations of data within different classes. Okay. So, it should not be an absolute value, it should be relative to the variance of data. Okay. So, accordingly, I can make use of the scatter or the variance to have some criteria function, the criteria function which has to be either maximized or minimized and when it is maximized or minimized, I can say that the separation between the two means that I have got, that is sufficient for classification. Okay. So, we can define the scatter of the projected data like this. So, let us see what is scatter of projected data. So, for an ith class, I define the scatter of the projected data as summation y minus m I tilde square, okay, where this summation has to be taken over all y belonging to set R 1. Is that okay? You find that this is something similar to variance. Okay. What we have not done is, we have not normalized this. Okay. So, when I define such a kind of scatter for the ith, for the samples belonging to set d I or the samples taken from class omega I, okay, then I can define the total within class scatter. Okay. So, that total within class scatter will be nothing but S I tilde square, or since we are considering only two classes, let me make it S 1 tilde square plus S 2 tilde square. Okay. Let us normalize this by the number of samples that I have, which is equal to n. Okay. So, this tells you the total within class scatter of the projected samples, right. And as I said that I want the separation between the two classes, or the distance between two means should be relative to this total scatter, right. So, I can define now a criteria function which is something like this: J w is equal to m 1 tilde minus m 2 tilde square upon S 1 tilde square plus S 2 tilde square. Okay. So, this S 1 tilde square plus S 2 tilde square, it is the total within class scatter, which takes into consideration the scatter of the samples taken from set R 1 plus the scatter of samples taken from set R 2. Okay. And what I have at the numerator is m 1 tilde minus m 2 tilde square, which is nothing but the square of the distance between the projected means m 1 and m 2. Okay. So, what I should try to achieve is this m 1 tilde minus m 2 tilde square should be as large as possible with respect to the total within class scatter, or effectively I want to maximize this criteria function J w, which is the ratio of m 1 tilde square minus m 1 tilde minus m 2 tilde square upon the total within class scatter. Okay. So, I want to maximize this. So, I can say effectively that this being the difference between two classes or two means, I can say equivalently that this is something similar to within class scatter, inter class scatter, okay, and this is something similar to intra class scatter. So, if intra class scatter is less, that indicates that your data distribution is very compact. If it is compact, then inter class scatter I need not have very large value to give the separation between two classes, right. Whereas, if this intra class scatter is large, that means the data are distributed sparsely or widely within every class. If it is so, then this inter class scatter should be quite large, so that I can have satisfactory classification performance, or I can discriminate between the classes very easily. Okay. So, effectively what I have to have is I have to maximize this criteria function J w, which is nothing but something like ratio of interclass scatter and intraclass scatter. Okay. And Fisher's discriminator actually maximizes this, and the value of w which maximizes this gives you the projection direction. Okay. So, how do I find optimal value of w which will maximize this? If I want to do that, in that case this expression I have to write as an explicit function of w, and then I take the gradient, or I take the differentiate it with respect to w, equate that to 0, and you get the solution. Okay. So, if I want to explicitly write this criteria function j in terms of w, let us do this. First, we define a scatter matrix. Scatter matrices, one is S I and other one is S W. I will say this S I is the scatter within the ith class, and S W is the total within class scatter, right. So, as before, I can define this S I, that is scatter of the samples within ith class, which is nothing but sum of x minus m I into x minus m I transpose, okay, where I have to consider this summation over all x belonging to class d I. Okay. So, this gives me the scatter of the samples in set d I, or the scatter of the samples which are taken from class omega I. Okay. So, once I get the scatter for individual classes or individual sets, then I can define total within class scatter, because this is within class scatter. So, I can define total within class scatter as S w is equal to sum of S I for all I, okay. And here we are considering only two classes. So, this will be S 1 plus S 2. Is that okay? Pardon? Total within class scatter. S 1 is the scatter of the samples in set D 1, S 2 is the scatter of the samples in set D 2. If I take these two sums, that gives me total within class scatter, or simply it is called within class scatter. Okay. Next, let us try to see that what will be the scatter of the projected samples. Okay. So, for that I define S I tilde square, which is nothing but W transpose x minus W transpose m I square of this, take the summation over all x belonging to set d I. Okay. So, earlier we have taken the scatter of the original samples, now we are taking the scatter of the projected samples. Okay. This expression can be written as, just by some reorganization, okay, I can write this expression as W transpose x minus m I into x minus m I transpose into W, okay, take the summation for all x in set d I. Okay. Now, given this, you find that this W, which is independent of x, I can take outside the summation, right. So, if I take outside the summation, then what I will have is W transpose, then summation x minus m I into x minus m I transpose into W, okay, where this W is outside the summation operation, and this summation I have to take for all x in set d I. Okay. Now, what is this term within the summation? This is nothing but S I, that is the scatter of the samples in the original space. So, what I simply have is this is nothing but W transpose S I W. Okay. So, when I have this, then the sum of these scatters over two classes, that is S 1 tilde square plus S 2 tilde square, that will be simply W transpose S 1 W plus W transpose S 2 W, okay, which is nothing but W transpose S 1 plus S 2 W, okay, and S 1 plus S 2, as we have already defined, that this is total within class scatter. S 1 plus S 2 is nothing but S W, which is total within class scatter. So, this simply becomes W transpose S W W, right. So, in the same manner, when I compute the difference between the two means, okay. So, that is nothing but, so difference between two means or separation of the projected means. Which is m 1 tilde minus m 2 tilde square of this, where m 1 tilde is nothing but W transpose m 1, m 2 tilde is nothing but W transpose m 2 square of this. I can reorient or reorganize this expression as W transpose m 1 minus m 2 into m 1 minus m 2 transpose W. Okay. And you find that this is something like between class scatter. Okay. So, we had this S 2 to be within class scatter, because for computation S omega to be within class scatter, because for computation of this I am considering the samples belonging to individual classes, computing their scatters and then adding these intra-class scatters. So, this is what is called within class scatter. Okay. And following the similar expression, this expression m 1 minus m 2 into m 1 minus m 2 transpose, this tells you something like between class scatter. Okay. So, I can write this expression as W transpose S B W, okay, where this S B we call as between class scatter. Okay. Now, we will find that this S W or within class scatter, this is symmetric and positive semi definite, and so is this between class scatter S B. Okay. That is the property of this scatter matrices. Okay. And not only that, when I am writing this expression as W transpose S B W, where this S B is M 1 minus M 2 into M 1 minus M 2 transpose. M 1 minus M 2 is nothing but a vector, row vector. M 1 minus M 2, sorry, this is a column vector, and M 1 minus M 2 transpose is a row vector. So, this is actually the outer product of two vectors. Okay. So, as it is outer product of two vectors, so rank of this scatter matrix S B will be at the most 1, not more than 1. Okay. And not only that, I can have some more observation about S B, or I can have some more observation about S B W. You find that when I consider this part, okay. Yeah. So, this portion M 1 minus M 2 transpose W, this is the inner product of two vectors, because this is a row vector, this is a column vector of same dimension. So, this term is inner product of two vectors. As it is inner product of two vectors, so it is a scalar. Okay. And when this is a scalar, this total term M 1 minus M 2 into M 1 minus M 2 transpose W, this being a scalar, this whole portion will be a vector, and the vector in the direction of M 1 minus M 2. Okay. So, when I am writing this as S B W, you find that this S B will be a vector in the direction of M 1, sorry, S B W will be a vector in the direction of M 1 minus M 2, because S B W is nothing but this, right. So, this S B W is a vector in direction of M 1 minus M 2. So, we will make use of this while solving for our projection direction W. Okay. So, I have these different scatter matrices and the corresponding expressions. So, once I have this, I have this within class scatter, I have this between class scatter, and what we said is that I should define a criteria function which is a ratio of measure of between class scatter and measure of within class scatter. Okay. So, now if I redefine our criteria function as J W is equal to, in earlier case it was M 1 minus M 2 square upon M 1 tilde minus M 2 tilde square upon S 1 tilde square plus S 2 tilde square, right. And we have found that this M 1 tilde minus M 2 tilde square is nothing but W transpose S B W, okay. And S 1 tilde square plus S 2 tilde square is nothing but W transpose S W W. Okay. So, I get an expression of this criteria function G A explicitly in terms of W is given by W transpose S B W upon W transpose S W W, where S B is between class scatter and S W is total within class scatter. Okay. So, what we have to do is we have to maximize this ratio by varying the vector W, and W gives you the projection direction. Okay. And that is a tedious mathematics. So, without going for tedious mathematics, let us see what is the solution. So, a W which will maximize this ratio must satisfy S B W is equal to lambda S W W for some constant lambda. Okay. So, the W which maximizes this ratio must satisfy this condition for some constant lambda. Okay. This expression, this ratio is known as generalized Rayleigh coefficient. Okay. And this expression SBW is equal to lambda SWW. It is nothing but a generalized eigenvalue problem. Okay. So, you find that if SW is non-singular, if SW is non-singular, then this expression will be simply in the form SW inverse SBW is equal to lambda times W. Okay. So, this is our well known eigenvalue problem. Okay. Where this W is nothing but eigenvector of SW inverse SB, okay, and lambda is the corresponding W is the eigenvector of SW inverse SB and lambda is the corresponding eigenvalue. Okay. But we can simplify our solution instead of trying to solve the eigenvalues and eigenvectors, simply because of the fact that SBW, as we said, that this SBW is a vector in the direction of M1 minus M2. So, by using this and from the relation that SBW is equal to lambda SWW, I can find out what should be the direction W, because as I said, the scale factor of W is not much important. What I want to see is what is the direction of W, that is my projection direction. Okay. So, from this you can easily find that W is nothing but SW inverse M1 minus M2. Why is it so? Because as we said that SBW is a vector in the direction of M1 minus M2. So, I can write this SBW as some scale factor k times M1 minus M2, because it is a vector in the direction of M1 minus M2, right. So, I can write this as some scale factor k into M1 minus M2, that is equal to lambda SWW. Lambda is a constant. Okay. So, I can put this constant under this constant k, because it simply becomes k upon lambda. Okay. So, equivalently I have some constant k 1 times M 1 minus M 2 is equal to S W W, right, which clearly says that this W is nothing but some constant k 1 times S W inverse into M 1 minus M 2. Is it okay? And as I said that the scale factor is not that important to me, because I am interested in the direction of W. The scale factors will indicate that how much will be the separation between the two classes, and in the projected domain how the points will be distributed. If I increase the scale factor, the separation will be more, the points will be more spreaded. If I reduce the scale factor, the separation will be less, points will be less spreaded. So, both of them, the separation between the classes as well as the variance in the projected domain, both of them vary simultaneously depending upon the value of k in the same scale. So, this scale k or k 1 is not that important. What is important is what is the direction w. Okay. So, as such I can ignore this scale k 1, and if I ignore this scale k 1, I simply have w is equal to S w inverse into m 1 minus m 2, okay, where this S w is total within class scatter and m 1 minus m 2 is a vector in the direction of line joining m 1 and m 2, right. So, if I use this projection direction for projecting the data into lower dimensional space, I can maintain the separation among the classes, and which is better for classification purpose. However, this particular projection may not be the best in terms of data representation as far as minimum squared error is concerned. Okay. So, what I have done is till now is a 2 class problem, and your classification design gets complete because what I have done is from multiple dimension I have projected onto single dimension. Okay. And in the single dimension I have to find out a threshold, so that if this one dimensional vectors or the scalars are less than the threshold, I will put them into one class. If it is more than the threshold, I have to put them into another class. So, I have to determine a threshold value, that is all. And the classifier which makes use of this concept is, as I said, is called Fisher's classifier or Fisher linear discriminator. Okay. Now, when I have C number of classes, I have to extend from 2 class problem to C class problem, and it can be shown that in that case it simply becomes C minus 1 linear classifiers, or the projection that now I am taking onto one dimension, I have to take projections onto C minus 1 number of different directions. Okay. So, the problem remains the same, simply it is extension from 2 dimension to C dimension, or the dimensionality of the feature vectors. Here it is one dimensional feature vector, and there we have to go for C minus 1 dimensional feature vector. And obviously, I will gain if C minus 1 is less than D, where D is the original dimensionality of the feature vectors, and C minus 1 is the reduced dimensionality of the feature vectors. Okay. So, we have discussed about this dimensionality problem and 2 ways to tackle the dimensionality problem. One approach tries to find out a projection which is the best in terms of data representation, that is the principal component analysis approach, and the other approach, that is this MDA or multiple discriminant analysis, is the one which is again a projection onto lower dimensional space, but it tries to guarantee that when you take the projection, the separability of the feature vectors between different classes, that will be maintained, which is not guaranteed by principal component analysis. Okay. So, we will stop here today. Next day we will start some other topic.